Hello everyone. So today's topic is string matching using suffix automata and bit parallelism. As the name suggests, we can see that suffix automata is like a category of automata which is accepting all the suffixes of a given pattern, right? And bit parallelism is very popular. Actually, this technique bit parallelism is very popular in nowadays because it is directly converting, it is not converting finite automata to DFA. Unlike other string matching algorithm using finite automata, they will convert NFA to DFA, but bit parallelism is directly simulating NFA by using bit of a particular pattern. So what is suffix automata? We can see that is like a deterministic finite automata of all the suffixes of a pattern. Same thing which we are talking about again, that we have to design DFAs, and designing DFA is very costly affair, because generally for a given pattern we are not getting DFA directly. We have to get non-deterministic finite automata first of the given pattern, and then that NFA will be converted into deterministic finite automata second. Then only you can apply DFA to the pattern matching. Otherwise, there is no way to apply DFA into the pattern matching. So what is solution? We'll use the solution later on. That bit parallelism is the one which is directly simulating the NFA. But let's consider the power of suffix automata. Like this is basically, it's very popular when especially your this kind of pattern where suffixes are also prefix. So this is very popular algorithm when you can get suffix and prefix in the same pattern. Second advantage of this suffix automata is actually this is searching the pattern and text from the right to left. It is not searching from the left to right. So right to left, this is always searching for a pattern inside the text from right to left. Actually, this is designing a directed acyclic word graph dog and for the given pattern. So let's understand what is suffix automaton. So if we can see the string, this is our string, x is a1, a2, a3 up to and so on an. So what are its suffixes? Suffixes, as we can see that its suffixes are this, and then a2 an and a3 an up to and so on epsilon. So these are its suffixes. So this is of course a regular expression. So all these suffixes. So what we have to do, construct n finite automata accepting all the suffixes, right? So how to get the suffix automata? We can design n finite automata for individual suffixes, and in order to accept this starting is this epsilon, we have to make starting state as a final state so that it can accept the empty string, right? And then after this conversion, we have to construct deterministic of individual non-deterministic finite automata, right? So suppose, for example, consider this pattern. Let's say AB, ABA. Consider this pattern, right? Okay. So what are the suffixes of this pattern? Suffixes are epsilon, then A, then BA, and then ABA, right? So so you know what is happening. Then we have to design a non-deterministic accept and make it final, because it is accepting the starting epsilon. Then make A, this is accepting another state, right? And then BA, then B and B, and then another one A, right? And this is another accepting BA, and then ABA, AB, then A. This is another accepting state, right? So we have three finite. Of course, we can cancel this and we can say that this is like A, B, A, B, and then A, B, A. This is another. So we have one finite automata, we have another, and we have third. We have three finite automata. In order to get its suffix automata, we have to convert this suffix automata into deterministic finite, because this is non-deterministic. You can see that from here we are getting A, and then also we are going from here on A. So this is non-deterministic. In order to get suffix automata, we have to convert this suffix automata into the deterministic form, right? Yes. And as we know that it is very costly affair, because converting non-deterministic to deterministic is very expensive affair. So look at here, same thing, we are getting the pattern AB, we can calculate all of its suffixes. Then AB is 1, and then BAB, and then AB another, and then BA. We have 1, 2, 3 and 4 finite automata, 4 NFA, and of course this is NFA. Look at here, A, then A, we have NFA. So in order to get the suffix automata, we have to convert this NFA into corresponding DFA. Then only we can use it into the string matching, right? So question is that how this the suffix automata can be used in the searching, right? So let's understand. Algorithm we will discuss later on. Let's understand. So you know there is a special algorithm, we call it directed acyclic word graph, BDM, backward dog matching. This is just name, backward dog matching. Backward in the sense that it is matching from the right, and D, dog directed acyclic word graph. Actually this suffix automata is known as directed acyclic word graph. So in this suffix BDM based approach, suffix automata based approach, we are constructing the suffix automata for the reverse pattern, right? Because we are interested in searching from the right, we are not interested in searching from the left. So we have to construct suffix automata for the reverse pattern, right? Yeah. So look at here, this is your pattern A, B, B, A, B, and let's reverse it. So once you reverse it, we will get B double A and then B B A. This reverse, and this is non-deterministic finite automata of this reverse pattern, right? This is non-deterministic finite automata for the reverse pattern. Yes. So after getting this finite automata for the reverse pattern, you have to convert into deterministic finite automata, and that deterministic finite automata is termed as directed acyclic word graph. Is it clear? Yes. So let me again summarize. Given a pattern, we will reverse it. After reversing it, you have to draw a non-deterministic for this, and that non-deterministic you have to convert into deterministic finite automata to get the directed acyclic word graph. This is directed acyclic word graph for the given pattern, right? Yes. So now this is what we call it, directed acyclic word graph. DOG is very popular in computer science. DOG, directed acyclic word graph. And now this is going to be used as a tool to the to match a pattern inside the test. You have seen that this pattern, whatever pattern we have designed, its DOG. Now pattern is no more existing, because in the pre-processing step we have to design the DOG of the given pattern. Let us consider the example. Yeah. Consider this pattern. Let's see, if we have this pattern and this is the text, we can see that this pattern AABB AAB is matching it over here, right? So this is the same DOG which I am writing over here. Initially, you know, we are taking two variable, one is last and position as beginning. As I said, in this approach, it's not like other approaches like KMP and Neo algorithm and Rabin car. We are always matching from the right. Reason is very simple, because we are reversing the pattern to get the dog of the given pattern. And once you reverse the pattern, then we have to start from the right. Is it clear? A, right? So A, if you follow this DFA, this A, we are reaching to the final state. That means A is also prefix of the given pattern. Look at here, A. Yes, A is prefix. Yes, A is matching, right? Then next one. So once you match to the final state, from last from 7, it will be decremented to 1. Last is becoming 6. Last, you will know very soon that what is the physical significance of this last. Then next one is A. So we have to get A and A here. A. From right to left, A and A. We are still going to the final state. That means A is matching. Yes, good. It is matching now, right? So last is again decremented by 1. Okay. Then again we have to go to this value and let's say A. Look at here, A and B. You are still reaching to the 4. A and B, but 4 is not a final state. That means BAA is not prefix. Yes, it is clear. It is not, but there is a transition, right? So if BA is not prefix, there may be possibility that you can get prefix later on, right? Then again go back, BA. Look at here, A, B. Then on next A is not defined. That means transition on A is not defined. So that means you have to suspend the scanning and record this last. You have to suspend the scanning and record this position which is last, right? So that means this BAA, right? That means BAA is not there. This is not there. So what was the last position? 5. Its meaning is very, very simple, that 2 to 4. That means next time these 5 they are not matching. So next time in this shift, this is 2 characters are matching. So next shifting we have to include these 2 characters and exclude these 5 characters. Look at here. So last is 7. Again every time you have to start the last from 7, right? And then position is 0 plus last. Last is position is this 0 plus 7, 5. So this position become 5. That means you have to go to the 5th position, 0, 1, 2, 3, 4 and then 5. This is the shifting, right? Again we had to adopt the same situation starting from B, last one. Yes, B, there is transition on B, but you know it is not reaching to the final states, no problem. Then again BA, then BA is still it is not reaching to the final state. You are here, and then BAA, you are reaching to the final state. Its meaning is very simple, that once you reach to some final state, means that this guy is a prefix of the given pattern. You can see AAB, yes, AAB is prefix of the given pattern. It's clear. So we have to record the position. Last is 7 minus 3 is 4, definitely. Total length of the window is 7. So it's 7 minus 3 is 4. So last is 4. Then again go back, BAAB, you are reaching here, not final, no problem. Then again BAABB, not final, yes. Then again look at here, BAABBA, not final, of course. Then if you are reaching to this and entire window is finished, like see BAA, BBAA, BAA, BBAA, yes, you are reaching to the final state and you are exhausted with the complete window, right? So what will happen, you have to shift it, position was 5, right? Position was 5 plus this lasts 4, right? So next one, you are shifting your window by 9th positions, right? Just like you are shifted by 5th character. Next time you have to shift by AAB, because this is prefix which is a suffix which is also prefix. Look at here, this pattern is having a suffix which is also a prefix. So this is intelligent algorithm which will utilize the suffix and prefix also. So next time if you are getting any next pattern, any like next character, let's say ABC, AB something, so definitely next shifting will be from here. Next shifting will be 3 and 3, 7. This will be the next window. This will be the next window, right? Yeah. So this is very good algorithm generally, and this is very popular and it was invented in 1998. So and we have seen that what is the major problem with all this finite automata and like the suffix automata. All the algorithm require finite automata NFA to be converted into DFA. You have seen it. You have to convert NFA and then that NFA need to be converted into DFA. So this is very expensive affairs actually. So because if you are converting NFA to DFA, it will consume your space, consume your time, and it is not very efficient. So researchers they have proposed the directly bit parallelism, and which is very popular nowadays, because most of the computers we have like 64-bit computer now, right? And we like 128-bit computer. Our computer word size is increasing day by day, and this kind of algorithm has tendency to process up to 64 length pattern at the same time. This is very good. And if your computer is increasing even up to 128 length pattern one at the same time, you know that 64-bit, like this 64-bit 64 length pattern can transmit at the same time, right, in a computer. So this is using bit parallelism. Actually you are not converting NFA into the DFA. This was like starting from 92, it was very popular. Initially it was not gaining the attention, but now it is gaining attention by the researcher actually. See, so what is happening with this algorithm bit parallelism? It is directly simulating NFA, no need to convert into DFA, and actually in the pre-processing phase it is converting pattern into the form of bits, right? And once you convert pattern into the form of bit, you can throw the pattern, right? And you can directly match text, match pattern against the text. Look at here. Yeah, no need to go to the description, you know it already. You see, consider this pattern, like see, consider P is ABAC, is very simple, ABAC, right? This is your pattern. So question is that how to make a bit table. This algorithm is making a bit table B, and B of A, actually this will consider BA, BB and BC, all the character. It will construct a bit table in the pre-processing phase, right? Once you have constructed the bit table in the pre-processing phase, you can throw away the pattern, no need of pattern for BA. You know this is bitwise A, yes, A is occurring at first position, so this will be 0, we will be writing from right. And then second is not A, it will be 1, third is A, it will be 0, fourth is C, it is not A, it will be 1. So this is basically, this is bit coding of A. and how long this bit can be? It can be up to 64 or it can be 128 depending on your word length of your computer, right? Same thing here, B of B, you can start first reading from here and assigning the bit from the right. B of B is 1, right? B is not first, then second, B is second, yes, then third is B, not B, third, fourth is also not B. Then B, C, C, first from left it is not C, it is not C, it is not C, and then this is C. This bit information is very important, right? So we can make bit information like this. Let's have another example like C. Okay. So let's have another example like pattern is A B C A A B, right? So what will be the bit combination for all this pattern? You see, B of A, yeah, bit combination B of A. We start from left and assign from the right. First one is 0, right? And then 1 1, then 0 0 and 1. This is B. This is sufficient for us not to convert the finite automata into DFA. Then B of B, right? B of B 1, then B is 0, then 1 1 1 and then 0. This is B of B. Then B of C, you can see that this is occurring at only one position. So 1 1, then 0 1 1 1. This is actually bit combination for all. If a pattern is not if a symbol is not in pattern, so all like see, if D is not here and if somebody is asking to find out the bit combination for D, it will be all 1 actually. It will be all. For simplicity, we are restricting up to pattern length only, but maximum limit of this can be up to the word length of a computer. Once you are done with this, right, so we can use the algorithm to match pattern inside the text. So what is that algorithm? So you see, this is the algorithm. D is D left shifted with 1 or B of particular text I, right? What is D? D is a state vector which is measuring, which is like storing the state of a finite automata, and this D is initially assigned as complement of 0, which is all 1, right? This is complement of 0, it is all 1. So left shift with 1 and bitwise R, B of text I. So you see this, no need to convert into DFA. Again I am talking about not converting, we are not converting into DFA. So after doing this, if we can see that mth minus 1th bit of D become 0, so we can say that pattern is found in the text. Look at here. And what will be shift? Because we are at step number I and pattern length is m, so shift will be I minus 1. Let's have one example. Yes. So P is ABA, right? Pattern is ABA. What is BA? Is very easy. BA is 0 1 0. You start from 0, then 1. BB is 1 0 1 and C is not occurring at all. So B of C will be all 1, right? Yes. So as I said initially, this D will be all 1 because D is complement of 1, complement of 0 which can be all 1. Yes. And initially this will be state vector, all bits will be 1. So we will start from A, we will start from A. Initially D is all 1, left shifted with 1 or BA here. Yeah. All 1, left 1 1 0, right? Or B of A is 0 1 0, right? So this is 1 1 0. Yes. So that means from triple 1 on input A, we can get to 110. Is clear? Yes. And we have seen that here, this means that we are done with 1. Same thing here, again next one we are getting B. So on 110 you are shifting with 1. So this become 100, or B of B, you can say that bit of B is 101. So this is 101, take bitwise R of this, we will see that this is 101. So that means we are getting the new state. We are not repeating with the new state. So 110, we are getting the new state, right? Yes. So again look at here. Next one is A again. So B of A, same value, we are like D is 101. So state is 101, and then it is left shifted with 1. So 101 is left shifted with 1. So this will be 010 or B of A 010. So this will be 010. Yes. So that means we are reaching to the 01. As I said that if after reaching to this, if this is 0, this means that pattern is found in the text. Which step? We got 3 steps, its length is 3, its shift will be 0. Shift valid shift will remain the same. This is giving another information, right? If we can see here, this is also 0 and first bit is also 0. First bit was representing A, right? First bit is also 0. This means this, right? In this situation that, okay, once you got ABA, up ABA, we get it. That means 2 bits are 0. That means A is also suffix and prefix. Look at here, A suffix and A prefix. So this is storing suffix and prefix information. Next, again, if we are talking about A, this while shifting 100, or bit of A, bit of 0, this is 110. 110, it is reaching to the old state. It will not create new state. It will be moving back and forth with the same state. Same state it will be moving, right? So yeah, so this is here again. And then after input C, we can see here after input C, since BC is all 1, it is reaching back to here, reaching back to here. Again we have to restart. It's very intelligent algorithm, very intelligent algorithms. Actually its complexity is of the linear time if your pattern length is less than or equal to word length. Let's have another example. Consider the pattern. Let's say, see this. This is pattern and this can be text. Text can be anyone, is not a problem. This is pattern A. So you see here 0 1 1 and then 0 1, right? Pattern B 1 then 0 1 1 0. Same thing. BC only one place. This is the situation, right? As I said that D is all 1 at initial position. That is D is complement of 0 at the beginning. No need to design the finite automata. D left shifted with 1, right? So just left shift with 1 or B of first pattern, first character A. So look at here class, you want all this thing. So it means that any position 0 indicate that we are done up to 1 character. That means yes, we are done up to 1 character. Yes. Same thing you have to left shift it again, right? And then B of next character is B. It's very simple. 0 indicate that up to 2 character we are done. Like this, see this. That means we are done up to 2 character. AB matches. And this is not 0. Had it been this is 0, it will also say that one more match is also there with 1 length. Same thing, you just left shift with 1, 1 1 0 1 0, always left shift with like 0 at the right. So this is B of C, and we have seen that B of C is 1 1 0 1 1. So you see, here is the answer. That means we are done up to 3 character, right? Yes. And then again D 10110 and or B of next character is A, right? B of A, and this is 10110. This is your answer. It's very simple. If you look at here, A B C A, yeah, and that means it is matching up to 4 character. This is matching up to 4 character. At the same time, this is also matching 1 character. Here up to this point, you can see that this is suffix and this is prefix. So this is always storing all the information. Again, if you look at here, this means that after reading A B C A B, we can see that this is matching entire pattern. Pattern is A B C A B, and at the same, because this becomes 0, at the same time this is also 0, which indicate that up to 2 character they are also prefix. Yes, they are also prefix. Look at here, AB and AB, they are also prefix. So this is storing suffix and prefix information, right? Thank you.